Why doesn't dark matter collapse? Think about it. Gravity pulls on it. There's a huge amount of it, outweighing all of the normal matter in the entire universe. So why doesn't it form dark stars or entire dark galaxies or even dark black holes? Instead, it just sits there in enormous fuzzy clouds around galaxies. And that is weird because normal matter collapses under its own gravity. It makes planets, it makes stars, it makes black holes. And it was after my last video about whether the center of the Milky Way could be a dark matter cloud instead of a supermassive black hole that so many of you then asked, if the dark matter cloud is the same mass as the black hole, why doesn't it also just collapse under gravity? So what is dark matter doing differently to normal matter? Well, in this video, we're going to unpack first why normal matter collapses under gravity in the first place, and secondly, the crucial reason why dark matter can't. Because if it could, the universe would look very different. Now, when I'm working on videos like this about dark matter or doing my own scientific research on supermassive black holes, I spend a lot of time going through research papers, reviewing figures and cross-referencing sources. I like to do all of that digitally as well so that I can actually, highlight key points, add notes, and just keep everything organized in one place. And that brings me to the tool that has recently made this process so much easier for me, UPDF. I can highlight key points, add sticky notes when I've had my own thoughts on the science, and if it's my own research paper draft, I can even redact information that's not yet ready to share. It keeps everything organized and in one place, whether I'm on my Mac or my iPad or my phone, because one account works across 4 devices. Plus, it handles practical stuff really well because unlike other tools, it actually lets you edit PDFs, so I can actually reorganize pages of a PDF, convert PDFs into other formats, and even use OCR to pull text from scanned documents. And add in the fact that UPDF's AI assistant is supported by GPT-5, then you've got an incredibly powerful tool that also costs about 1/6 of the price of Adobe Acrobat. That is a massive saving. So if, like me, you work with PDFs every single day, you've got to check them out. I've popped a link in the description down below that gets you a limited time offer for UPDF. So, a big thanks to UPDF for sponsoring this video, and now let's dive into all of this and chat first about why normal matter collapses under gravity in the first place. So let's start with the simplest scenario that we can think of, right? A bunch of normal matter particles just randomly strewn about, none of them moving initially, but then with the only force acting upon them, gravity. If all you have is gravity attracting each particle to every other particle, then yes, your cloud of particles slowly gets denser and denser in the center until it's so heavy that not even light can escape, and it does collapse and form a black hole. But that is an incredibly simple model, one that has 2 very unrealistic problems. First of all the particles won't be stationary at the beginning. Each particle will have some inherent energy to it, which means they'll all be moving to start with. And then second of all, gravity is not the only force at play in the universe. We also have the strong force that binds the centers of atoms together, and the electromagnetic force, which deals with the interactions between charged particles. So opposites attract, holding negatively charged electrons in orbit around positive protons in the center of atoms. Whereas like charges, like say 2 positive protons, will then repel each other. Plus, any moving charges you have are also going to set up magnetic fields, which again can deflect particles, but are also responsible for powering motors, generators, and a bunch of electronics. And the cherry on top is that light itself is an electromagnetic wave. From radio waves through to infrared to visible light that we can actually see with our eyes and out to very energetic X-rays. They are all light waves created by one electric and one magnetic field oscillating in space, which carries away energy, radiating energy. All light waves are radiation. And crucially, particles can radiate their energy away as electromagnetic waves, losing heat when cooling down, but also gaining heat, gaining energy as they absorb radiation, as they absorb light. So if we take a more realistic gas cloud now, one where the particles have their own inherent energy, which means they're moving to start with, then as gravity initially starts to take hold and squish the cloud down slightly, the number of interactions and collisions between particles increases, giving some of the particles more energy than they started with, increasing the temperature and therefore the pressure in the cloud of particles. It means that the particles in the cloud actually have more energy to resist the pull of gravity down. And so the cloud expands again because of its own energy, which reduces the temperature and reduces the pressure, and resisting that direct collapse under gravity that would otherwise happen. So to actually get normal matter to collapse, it has to be able to radiate some of that energy away as heat. So if you do get two particles that collide and convert their movement energy, their kinetic energy, into that internal inherent energy, it can then radiate that away as an electromagnetic wave, as light, as radiation, as heat, allowing the particles to cool down and for gravity to eventually again take hold and continue the collapse down into a star or a planet or a black hole. If there is no electromagnetic force, then there is no collapse, because the cloud of particles never cools enough for gravity to be able to overcome the inherent energy in the gas cloud. Which brings me to part 2, the crucial reason why dark matter can't do this. Dark matter is matter that we cannot see, so it doesn't emit light or reflect light or absorb light and trap it away like a black hole. The only reason that we know that dark matter is there is because of the effect that it has on the objects that we can see around it. It's the same way that we can't see wind, but we know that it's windy because we see the trees and other objects that we can see move. And so when we do that and map out where is all the dark matter in the universe, we find that it makes these big fuzzy structures, like diffuse halos of dark matter around galaxies of stars, all interconnected by long fuzzy filaments of dark matter that span the entire universe in what's known as the cosmic web. I've made a video before on all the evidence we have for dark matter. I'll link it below if you want to check that out. But what us not being able to see dark matter means physically is that dark matter, whatever it is, does not interact with the electromagnetic force. It means that a cloud of dark matter particles doesn't have any way to radiate away that energy to allow gravity to take hold in the same way that normal matter does. Or does it? Because lucky for dark matter, the universe is also expanding. So when we look out at distant galaxies, they all appear to be moving away from us because the space itself in between them is getting bigger, spreading out the energy. So in the same way that photons, particles of light moving through space as an electromagnetic wave, lose energy by having their wavelength stretched out to a lower energy light in what's known as a redshift, dark matter particles can lose energy as the universe expands, which allows them to cool just a little bit. Which means that while dark matter doesn't clump together and collapse under gravity to the extreme like normal matter does to make black holes and stars and galaxies, instead it clumps together just a little bit to be able to make these huge diffuse structures like halos around galaxies and filaments in the cosmic web. This was actually predicted by computer simulations of the entire universe that contained dark matter back in the 1980s and 1990s, but the cosmic web itself wasn't observed with telescopes until the late 2010s. So even just the sheer existence of the cosmic web is yet another piece of evidence in the pile in favour of dark matter existing in our universe. Check my microphone was actually recording. Yes, done that before. Ugh. If there is... Pip. Where'd it go? Oh, it's on me. Yeah. Along with about 100,000 other pip hairs in my own hair still.